Okay. Next is about solution of differential and difference equations. Why it is needed? A solution of differential and difference equation. When we are going to represent the equation, it is in terms of a differential equation or else difference equation. Differential in terms of your continuous time, difference in terms of your discrete time signal. For that reason, it is very important. And also in second module, we learnt what do you mean by a differential and what do you mean by a difference equation, or what are the equations is going to be when we are going to solve the problems on a signal. Okay, here the frequency response is the amplitude and the phase change of the system imparts the complex sinusoidal amplitude and also of the phase a signal it is consisting of, that is the frequency response. Okay, this indicates that frequency response is for the steady state it is going to be taken, and a few more information about the, what do you mean by a steady state parameter when you're going to design any of the system which is operating by its own manual based on the direction or else the signal what you are providing, like your remote car. What is the instruction you are going, whether it is a forward movement or reverse, which side you are going to turn your car, right? You learn of those why it is the signal how it is going to passing from previously it was a wire connection to your motor car and to the remote what you are going to use. Nowadays it's a wireless communication, right? How a signal is going to be passing and what should be the initial conditions so that I can go for, so that movement of a device it can be controlled by the one more device, that is remote and a car, how it is going to be interrelated. Those all will come across in your higher way, you just will see what it is going to be. These are in terms of equation way we are learning in the signals and in your control systems or DSP, what we are going for, what is the equation we are going for, and those all will be running a small chip. Whatever I'm telling of this differential difference, whatever the equations we are telling, it's by manually, but in the system if I'm uh, speaking and you are seeing of these all different parameters on your mobile, this all thing a signal is processing, and each fraction of second it is processing. If I'm making any movement here on the board or if I'm making some hand movement, it's all capturing and it is represent to you, right? That's all in terms of what is mathematical operations are going for, that we are learning SNS control system and DSP. Okay, that's what the interrelation. For that reason this is steady state response, you learn more there. Okay, it should be in a sinusoid, that you just keep in mind. Then in contrast to the differential and difference equation descriptions for the system, the frequency response description cannot represent initial condition. Here, initial condition, some application result, what you are giving the input, that only you should get. That's what the minimum steady state. Okay, then the differential equation representation for a continuous time system is going to be taken as summation k is equal to 0 to n a k d k y of t divided by dt power k is equal to summation k is equal to 0 to m b k d power k x of t divided by dt power k. Taking Fourier transform on both sides for difference equation, it's going to be changing here only at this position, that is j omega power k y of j omega and j omega power k x of j omega. Okay, then taking the frequency response h of j omega is equals to output to the input y of j omega divided by x of j omega, that is going to be equals to summation k varying from 0 to m bk j omega power k divided by summation k is equal to 0 to n ak j omega power k, where h of j omega is called as a frequency response of the system. Thus, the frequency response of a continuous time LTI system described by the linear constant coefficient differential equation is the ratio of the two polynomials in terms of j omega. Alternatively, if we have frequency response of a continuous LTI system as a ratio of the polynomials in terms of j omega, we can determine the corresponding differential equation. If we know what is the frequency response about output and to the input, what is the relationship between of those, I am able, if I know about that, I can find out what is the frequency response of the whole system, what you are going to perform some of the operations, right? In the same way, the difference equation representation for a discrete time LTI system is given as summation k is equal to 0 to n ak y of n minus k is equal to summation k is equal to 0 to m bk x of n minus k. This is actually this difference equation is going to be coming under module 4, but now only I will discuss about this. Just you, after the completion of the fourth module, the properties and all, you can go through this, but I will finish off this part, only small part is there, so for that reason. Okay, taking a DTFT on both side, DTFT is instead of going for here it is taken as j omega. In this case, we will be writing in terms of e raised to minus j omega power k y of e raised to j omega, that is equal to only for x of n minus k, that is e raised to minus j omega power k x of e raised to j omega. Here also h of e raised to j omega it is about frequency response, that is equal to y of e raised to j omega divided by x of e raised to j omega, that is equal to summation k is equal to 0 to m bk e raised to minus j omega power k divided by summation k is equal to 0 to n ak e raised to minus j omega power k. The discrete time system, the frequency response is the ratio of the polynomials in terms of e raised to minus j omega. Okay, these polynomials. Then alternatively, we can, if we have a frequency response in terms of discrete time LTI system as the ratio of polynomials e raised to minus j omega, we can obtain the corresponding difference equation. Means the equation should be in terms of e power j omega. In the previous way, it is in terms of j omega, right? Then about frequency response of the LTI system. Then we will define what is that frequency response is going to be. The relationship between the time domain representation and the frequency domain representation of the LTI system are going to be discussed in this LTI system. Analyzing an LTI system in frequency domain is easy due to many factors. One among these is convolution in time domain transforms to multiplication in frequency domain. In the properties, we come across that x of t convolution with y of it's going to be y of j omega, right? That's what the main importance when I am going for using of my LTI system. That is, the output of the system is obtained just by multiplication of the Fourier transform. Convolution is somewhat different. We have to apply the formula and we have to apply the limit further. But when I am going to consider of the multiplication, it is just a multiplication of two factors, right? For that reason, it will be easy to process. Processing is very important, right? That's what the reason. Fourier representation of the input with the system frequency response. Then the frequency response is the amplitude and phase change in the system imparts the complex sinusoidal. Then the impulse response is going to be the impulse response and frequency response of the continuous time and discrete time LTI systems forms ft and dtft pairs respectively. Here h of t, when it is a Fourier transform, you will be getting as h of j omega, and h of n, the dtft, the discrete time Fourier transform, that is you will be getting as h of e raised to j omega. Okay, For continuous time system having impulse response h of t and input x of t, the output is given as y of t is equal to x of t convolution with h of t. Taking Fourier transform on both sides, you will be getting as y of j omega is equal to x of j omega into h of j omega. Then if I write in terms of h of j omega, that is equal to y of j omega divided by x of j omega. Now h of j omega is known as the frequency response of the system. For this is for the continuous time. When I go for the discrete time LTI system, having the impulse response h of n and the input x of n, the output y of n is given by y of n is equal to x of n convolution with h of n, and taking dtft on both sides, y of e raised to j omega is equal to x of e raised to j omega into h of e raised to j omega. Then h of j e raised to j omega is going to be equal to y of e raised to j omega divided by x of e raised to j omega. H of j omega is known as the frequency response of the system. So about a small theory about frequency response and differential and difference equation. Next we will solve the problems based on frequency response. Here the first problem is find the frequency response of a continuous time LTI system is equal for a transform equation, that is h of j omega is going to be equal to, we know this equation. What is that equation? Integration minus infinity to plus infinity h of t e raised to minus j omega t dt. Then here substituting for h of t is e power minus mod of t. Mod of t means it is consisting of both negative values and also positive values. For that reason, the integration is divided into for the negative values and also for the positive values. Here it is taken as from minus infinity to 0 e power minus of minus t. For that reason plus t. Getting this, already minus is there for the negative values of minus t. Minus of minus plus t e raised to minus j omega t dt plus from 0 integration 0 to infinity e power minus into plus minus e raised to minus j omega t dt. Then adding of the powers here. Then e power 1 minus j omega into t dt plus 0 to infinity e power minus 1 plus j omega t dt. That is going to be equal to 1 divided by, do the integration and apply the limit, you will be getting as 1 divided by 1 minus j omega plus 1 divided by 1 plus j omega. That is, you will be getting as h of j omega is going to be equal to 2 divided by 1 plus omega square. Take the LCM and do that. You can go with the basic maths. You can do of that. Okay. Then about the next problem. Obtain the frequency response of a continuous time LTI system whose impulse response is h of t. Here it is varying from at minus 1 the amplitude is of minus 1, at 1 it is minus 1, at 0 it is 1. This is what h of t signal they given in terms of a graphical representation. From this we have to write what is our h of t. What is h of t? Is going to be, that is equal to minus, this is minus, observe here, minus amplitude is of minus 1. I can, what is this at position of this? Observe here the graph is in terms of arrow. It is indicating that it's a impulse response, right? Impulse response. I can write delta again at the right side. It is of minus because amplitude is of minus delta t minus 1. I hope you got this, how we wrote this equation. Then the frequency is given by minus infinity to plus infinity h of t e raised to minus j omega t dt. Then substituting h of t equation, what is that equation? Just here it is written. Then already used, we come across what is delta of t of a Fourier transform is going to be, for the first function it is going to be taken as minus e raised to j omega. For second function at 0 only you will be getting as 1 only. Then minus e raised to minus j omega using of the shifting property. Okay, already we come across a small problem there. From that you can write out this. Then here it is written as taken one this side and remaining part other side. So I can write as 1 minus, taken minus also common, e raised to j omega plus e raised to minus j omega. Then multiplied and divided by 2 here. This. Then what I can write, it is plus is there, means this 2 cos omega, 1 minus 2 cos omega you will be getting off. That is one problem. Next, the impulse response of a continuous time LTI system is given by h of t, that is equal to 1 divided by RC into e raised to minus t divided by RC into u of t. What the question it is asked, find the frequency response and also plot magnitude and phase response. Then the solution is going to be h of j omega is equal to integration minus infinity to plus infinity h of t e raised to minus j omega t dt. Then substitute for h of t, what is the given equation, that is 1 by RC e power minus t divided by RC into e raised to minus j omega t u of t dt. What is the limit is going to be, based on u of t function the limit is going to change from 0 to infinity, and 1 by RC is constant, that is taken outside. Remaining part is of integration 0 to infinity e power minus t divided by RC e power minus j omega t dt. Then taking the powers you have to add here, take minus sign outside, you'll be getting as 1 divided by RC plus j omega t is taken outside dt. Then here just interchange the terms, first written as j omega plus 1 by RC. Okay, solve for this and apply the limit for this, you'll be getting as 1 divided by RC divided by j omega plus 1 divided by RC. Then what is the magnitude, it's going to be 1 by RC is a constant that you have to keep as it is, and denominator part square root of real square and imaginary square, that is omega square plus 1 divided by RC whole square. Then when you plot the graph for this, you'll be getting like this. At 0 you'll be getting as maximum as 1, at minus 1 by RC and at 1 by RC you'll be getting as 1 divided by root 2. Just you substitute here omega values, then you'll be getting this graph. Then what about the phase? Numerator you will not get, a phase will be 0. For the denominator you'll be getting as phase response h of j omega is going to be minus tan inverse omega RC. Imaginary is of omega divided by 1 divided by RC, means omega RC you will get. The same thing here it is written. Then the phase angle is going to be at 0 you will not get any angle, at minus 1 by RC pi by 4 you will get, and again here this side 1 by RC you will be getting as minus pi by 4 and by 2 it will is asked, all the questions is asked, but this question is asked repeatedly. Okay, then next problem is of draw the frequency response of the system described by the impulse response h of t is equal to delta of t minus 2 into e raised to minus 2t u of t. the frequency response is going to be h of j omega is equal to integration minus infinity to plus infinity h of t e raised to minus j omega t dt. What is h of t equation? Here the equation, you just substitute here, then multiply a delta of t with e raised to minus j and the 2 e raised to minus 2t u of t with the e raised to minus jt and take the limit for both. Then what I will be getting, minus into plus infinity delta of t e raised to minus j omega t dt is minus e raised to integration minus infinity to plus infinity 2 into e raised to minus 2t e power minus j omega t dt. Remember, delta of t Fourier transform is going to be 1. Okay, that's what you can directly write, that it will be 1 only. Minus 2 taken outside, integration based on our u of t function, we can write the limit here as 0 to infinity e raised to minus 2t e raised to minus j omega t dt. Then add the powers here, therefore you'll be getting as minus 2 plus j omega into t dt. Then integrate this, apply the limit, you'll be getting as 1 minus 2 into 1 divided by 2 plus j omega. Then take the LCM and do the modification, you'll be getting as j omega divided by 2 plus j omega. What is the magnitude? Here only omega, imaginary part is there, so you'll be getting as square root of omega square, square root square get cancels, so you'll be getting as omega only, divided by square root of real is of 2 square 4 plus j omega square, right? You'll be getting of. Then about phase response, only imaginary is there and real is not there, means it will be infinity, tan inverse infinity is pi by 2 and minus denominator part is going to be tan inverse of omega by 2. Therefore the magnitude and phase spectra is going to be coming like this. It's at 0 it will be 0 and again it is going on increasing, and angle within pi by 2 in the positive way only it is changing. That is about the phase and magnitude of the given problem. Okay, from this we completed the third module.